Hello everyone, this is Geometry, lesson 6-4, proving a quadrilateral is a parallelogram. In this lesson, we'll be able to use properties of sides, angles, and diagonals to identify a parallelogram. Let's look at explore and reason. Sketch the quadrilaterals as described in the table, include the diagonals. Quadrilateral 1 has 0 pairs of parallel sides, so none of the sides are parallel. And it has 2 congruent pairs of congruent sides. So 2 sides are congruent to each other, and the other 2 sides are also congruent to each other in terms of length. Quadrilateral 2 has 1 pair parallel sides and exactly 1 non-parallel pair. So 1 pair parallel, 1 pair congruent sides. Okay, it doesn't have to be the pair that's parallel, but it has to be exactly one. It has to be exactly 1 non-parallel pair. So whatever the pair is parallel to each other, the other 2 sides that are not parallel need to be congruent. Quadrilateral 3 has 2 pairs, so all the pairs are parallel, and the 2 opposite pairs are congruent. Okay, so these are the conditions for quadrilaterals 1, 2, and 3. Part A, we're going to measure the angles of each quadrilateral. How are the angle measures in quadrilateral 1 related to each other? In quadrilateral 2, in quadrilateral 3. Okay, so you want to first sketch examples of quadrilaterals 1, 2, and 3. There may be more than one example that you could think of. See if you see any patterns by drawing the figures. Okay, you can use a ruler to mark 2 equal perpendicular distances to draw a parallel line. And you could also use a ruler to draw congruent sides of the same length. But today, let's look at a new tool called Geogebra. This is another great tool for graphing. It also has graphing calculator and other calculators. We're going to use something called, so go to geogebra.org. Okay, and then go to Geometry app. Okay, or you could just type in geogebra.org/geometry, and you'll be able to just draw figures on the coordinate plane. So let's try drawing quadrilateral 1. I'm going to draw a segment. You need to have 0 pairs of parallel sides. None of them are parallel, but you have 2 congruent pairs. All sides need to be congruent to another side. Okay. 2 consecutive pairs, which mean they need to be connected. So if you have this, consecutive lines are right next to each other, so they're adjacent. So you have 2 congruent sides, but the other 2 the other pair of sides also need to be congruent, but they cannot be parallel to them. So you cannot make a square, but you can just make something else that's equidistant from your other 2 points here. Okay, so A, B, and B, C, they're congruent, and AD and CD are congruent, but there are no parallel sides. Okay, this is just one example. And we can say that's quadrilateral 1. Okay, and what about quadrilateral 2? Can you give an example? 1 pair needs to be parallel, and the other non-parallel pair needs to be congruent. So you can think of a trapezoid, right? Trapezoid has two bases that are not congruent to each other, but they're parallel. And the other two legs are congruent. Okay, this could be one example for quadrilateral 2. What about quadrilateral 3? Two pairs need to be parallel, so it's a parallelogram. And two opposite pairs need to be congruent. So like opposite pairs are the non-consecutive sides. So you can say these two are opposite sides that are congruent. How about let's make it longer so that it's not a square and we know the difference between them. So I'm gonna make that longer. Whoops. Okay, let me erase that. I to J is here and K to L is here, okay? And then the other two opposite sides are congruent and they're parallel. So it could be a rectangle. Okay, so you already see what types of parallelograms that quadrilaterals 1, 2, and 3 would usually form or always form. Okay, you can easily see that quadrilateral 1 would satisfy when it's a kite. And quadrilateral 2 would have trapezoids that could satisfy the conditions well. Quadrilateral 3, rectangles could satisfy the conditions for quadrilateral 3. Okay, so now measure the angles of the quadrilaterals. How are the angle measures in quadrilateral 1 related to each other? So here you have angles A, B, C, and D. You can see that B is a right angle. D, the opposite angle, is an acute angle, but angles A and C are obtuse angles. So they're greater than 90 degrees. Okay. So you have one pair of opposite congruent angles, A and C. Okay. You will actually always get one pair of opposite congruent angles. Quadrilateral 2, you have for the trapezoids, your base angles are congruent, right? So you have base angles that are congruent. The other two angles, the angles that share a leg, like EG or FH. So angles E and G are supplementary. F and H are supplementary. So the angles that share a leg are supplementary. They make 180 degrees because that's a transversal to two parallel lines. And same side interior angles are supplementary. Quadrilateral 3, for rectangles, opposite angles are congruent. Okay, they're all right angles for this rectangle. Consecutive angles are supplementary. Okay, so that's true for all rectangles, but if you have other quadrilateral examples for quadrilateral 3, except for a rectangle, then you should have opposite sides, opposite angles that are congruent, but consecutive angles that are supplementary. So for example, another example for quadrilateral 3, you could have M and N that has a one as a slope, and then OP with the same slope. So they're parallel and they're congruent. Opposite lines, opposite pairs are congruent and parallel. And same for MO and MP. They are exactly the same distance and they're also parallel. So this could also be an example for quadrilateral 3. So it could be any parallelogram. Okay. In this case, M and P, angles M and P, the opposite pairs are congruent. N and O, they're congruent because they're because we got two parallel pairs. And then consecutive angles, N and P, M and O, they're supplementary. They make a line. Okay, so let's summarize that and write it down in part A. I'm going to add text now so that you guys can better recognize my handwriting. So quadrilateral, one pair of opposite congruent angles. Quadrilateral 2, base angles are congruent. Angles that share leg are supplementary. Okay. Where do I go? Okay. Quadrilateral 3, opposite angles are congruent. Consecutive angles are supplementary. Okay, so this is for part A. Okay, measure the diagonals of each quadrilateral. How are the diagonals in quadrilateral 1 related to each other in quadrilateral 2 and 3? So if you draw quadrilaterals, okay, B to D. Okay, I'm just gonna draw. Okay, B to D and A to B. BD and AC are diagonals, right? Okay, so how are they related? For quadrilateral 1, diagonals are perpendicular because it's a kite. One diagonal bisects the other. So BD bisects AC. If that's M, AM and CM is congruent, but not BM and DM, okay? Diagonals are not congruent. This one, BD is longer than AC. Quadrilateral 2, diagonals are congruent. EH and FG are congruent. Okay, same distance. Quadrilateral 3, diagonals could be congruent when it's a rectangle, but is it always congruent? No, NP here is gonna be shorter than NO here, right? So not always, but the diagonals bisect each other. They cut each other in half, and diagonals are not always congruent, okay? So let's write that down in part B. So quadrilateral 1, diagonals are perpendicular. One diagonal bisects the other. Diagonals are not. Okay. And then, let me move this over here. Or where could I go? Quadrilateral 2, diagonals are congruent. and quadrilateral 3, diagonals bisect each other. Diagonals. Okay, let me find another space. Why don't I move this up? Okay, that's B. Okay. Part C, compare the relationships among the angles and diagonals of quadrilateral 3 to those of the other two quadrilaterals. Are there any relationships that make quadrilateral 3 unique? Okay, so look at the relationships among the angles and diagonals for quadrilateral 3. Can I highlight these? Nah. Okay. So look at quadrilateral 3 here. Look at quadrilateral 3 here. Are there any relationships to make quadrilateral 3 unique? Well, the opposite angles are congruent, consecutive angles are supplementary, and diagonals bisect each other and they're not congruent. So you can say they all have at least one pair of congruent angles, right? All the quadrilaterals. Only quadrilateral 3 has what? 2 pairs of opposite congruent angles, okay? And diagonals that both bisect each other, okay? Only quadrilateral 3 has 2 pairs of opposite congruent angles and diagonals that bisect, that both bisect each other. So both pairs are unique. So let's write that down for part C. They all quadrilaterals have at least one pair of congruent, but only quadrilateral 3 has 2 pairs of opposite angles and diagonals that both bisect each other. Okay. There you go. All right, so let's think about what properties determine whether quadrilateral is a parallelogram. We're going to learn about parallelogram today. Example 1, investigate sides to confirm a parallelogram. In quadrilateral ABCD, AC is a diagonal and AB is congruent to CD, AD congruent to BC. Is ABCD a parallelogram? We're not given that the two opposite pairs are parallel. We're just given that AC is a diagonal. So we want to prove if ABCD is a parallelogram. You can prove it by the converse of alternate interior angles theorem because BC and AD are parallel. Wait, it must be a parallel line when you have angles, alternate interior angles that are congruent. So first, in order to have the information that the alternate interior angles are congruent, first you need to identify the two triangles ABC and CDA. And you can say, oh, they're congruent by SSS. And AC is congruent to itself by the reflexive property. So they're congruent. By CPCTC, BAC is corresponding with DCA, so they're congruent. And BCA is also corresponding to DAC. So these two angles are congruent. And they're both alternate interior angles. And if all the alternate interior angles are congruent by the converse of alternate interior angles, they must be parallel, right? AB and CD must be parallel. AD and BC must be parallel. So by definition, we have two pairs of parallel sides, and it's a quadrilateral that is a parallelogram. Okay, so try number 1. Explain why you cannot conclude that ABCD is a parallelogram. When you just look at it, you just know the sides are not parallel. AB and CD, they're not parallel. DC, they're not parallel. AD, BC, they don't look parallel. But how can you conclude with the given information? Okay, because we have BC congruent to CD. We have AB congruent to AD. And you can try going through the same method here. You can try saying, oh, this triangle and that triangle must be congruent by SSS, right? Triangle ABC must be congruent to triangle ADC, okay? By SSS, because AC is congruent to itself by reflexive property. And then by CPCTC, angle BAC must be congruent to angle DAC. So these two angles are congruent. And angle BCA must be congruent to angle DCA. These two angles must be congruent. But does that prove that those are parallel lines? No, the alternate interior angles are not congruent, right? So how can you say they're not congruent? Even though AC is a diagonal of quadrilateral ABCD, both pairs of opposite sides are not congruent. So ABCD is not a parallelogram. So just by trying to prove with the same logic, it doesn't work. And you can say alternate interior angles are not parallel, not congruent. So there's no way to prove. You can say, or you can just simply say that even though AC is a diagonal of quadrilateral ABCD, both pairs opposite sides are not congruent. So ABCD is not a parallelogram. So we're thinking about the condition back here. Quadrilateral 3 was actually describing parallelograms. You need to have two parallel sides and two opposite pairs that are congruent, right? So the opposite sides are not congruent, so it's not a parallelogram. But you can use this method in example 1 to prove it's a parallelogram. In order to prove it's not a parallelogram, you can just use the conditions so that it's easier to say, oh, it just doesn't satisfy the condition. Okay, so we have a theorem 6-11, Converse of Theorem 6-7. If both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is parallelogram. So if you have this condition, both sides, the opposite sides are both congruent, then it must be a parallelogram. Okay. Example 2, explore angle measures to confirm a parallelogram. Let's explore and see if we could understand the properties of parallelogram. Part A, Teo sketches a design of a quadrilateral shaped building. If angle 1 is supplementary to angle 2 and 4 is his design of parallelogram. Okay, so let's use logical reasoning to see if it's a parallelogram or not. If angle 1 is supplementary to 2 and 4, 1 plus 2 is 180, 1 plus 4 is 180. Okay, right? Since 1 and 2 are same side interior angles and they're supplementary, these two must be parallel, right? Top and bottom sides are parallel. And since 1 and 4, they're same side interior for the shorter opposite sides, the left and right sides are parallel because this is now transversal. And so since they're both parallel, the opposite pairs are parallel, it's a parallelogram. It is a parallelogram. Part B, Teo sketches a second design in which 1 is congruent to 3 and 2 is congruent to 4. Is this a parallelogram? The sum of interior angles must be 360 for quadrilaterals. And so if you add all of them to get 360, and you know that 1 and 3 are congruent, 2 and 4 are congruent, you know you can use algebra to figure out that you can substitute either way and say either 1 plus 2 is 180 or 1 plus 4 is 180. Okay, either way. Substitution works either way. Okay, and you can say that it works for either way. You can substitute 2 with 4 and 4 with 2 because the opposite angles are congruent, right? Because this now has the same condition with part A, you can say that the second design is also a parallelogram. Okay, so once you know both opposite angles are congruent, or the same side, the consecutive angles are both supplementary to each other, then it's a parallelogram. So let's try number 2. Is DEFG a parallelogram? Explain. And part B, is element O a parallelogram? Explain. So if you can do it by yourself and see if you can explain by yourself, come back when you're ready for answers. Okay, part A. Is this a parallelogram? You have 153 for E, G is 153, and F is 27. So D must be also 27, right? 360 minus all these would be 27. And also 27 is supplementary to both G and E. So D must also be supplementary to the other two consecutive angles. And so since the opposite angles are congruent, and you have same side interior angles that are supplementary, both pairs of opposite sides must be parallel to each other. So yes, it is a parallelogram. Because ABCD has two pairs of opposite angles that are congruent. Okay. Part B, is LM and O a parallelogram? You can see that L is slightly smaller than M, the angle, and the opposite angles are not congruent. You have same side interior angles that are congruent, but does that make the opposite pairs parallel? No, same side interior angles must be supplementary in order for the opposite lines to be congruent, to be parallel. So this doesn't prove that the opposite sides are parallel, and they're actually not a parallelogram. None of the angles is supplementary to both of the angles consecutive to it. So no. And explain. None of the angles is supplementary to both of the angles consecutive. Okay. All right, so we got more theorems here. Converse of Theorem 6-8 says if an angle of a quadrilateral is supplementary to both of its consecutive angles, then quadrilateral is a parallelogram. And if both pairs of opposite angles of a quadrilateral are congruent, then it's a parallelogram. So these two conditions we looked at in the explore section, right? These are the conditions we needed to have for quadrilateral 3, remember? And these are going to make a parallelogram. Example 3, find values to make parallelograms. Part A, for what values of R and S is W, X, Y, Z a parallelogram? Okay, so now we're going to use algebra and algebraic expressions to figure out some variables. Knowing the properties of parallelograms, we know that X, Y, and Y, Z, X, W, and Y, Z, X, Y, and W, Z, X, W, and Y, Z, the opposite pairs need to be congruent. So you can set them equal to each other and solve for the variables. Okay. And so 4R plus 7 is equal to 7R plus 1. Solving for R is 2. Same way, you set up the algebraic expression for X, Y, and W, Z. You solve for S, and that's 7. And don't worry about having different variables for the opposite sides. Then it's non-solvable. You're probably not going to find a problem like that in the math class in here, maybe in real life. Part B, for what values of A and B is RSTU a parallelogram? Now we need to use the property that the opposite angles must be congruent. So you can set up another expressions. 5A equals 3A plus 14, and 3B plus 37 is equal to 4B plus 1, and solve for the variables A and B. A is 7, B is 36. Okay, so this is algebra plus geometric properties that you just learned. So let's see if you can use algebraic skills with the geometry skill you just learned to solve these problems. Try number 3, A and B. See if you can do it by yourself. Come back when you're ready for answers. Okay, if X is 25 and Y is 30 is PQRS parallelogram. You just need to check if they're equal to each other. Okay, the angles, the opposite angles need to be congruent to each other, right? So Q must be congruent to S. That means 5Y minus 10 must be equal to 3Y plus 50. And if Y is 30, 5 times 30 minus 10, so you substitute 30 to Y to see if the numbers are congruent. 5 times 30 is 150 minus 10, and 3 times 30 is 90, and then you add 50. 150 minus 10 is 140. 90 plus 50 is 140. Are they equal to each other? Yes. So check. You're still not done. You still don't know if they're true for P and R. 2x minus 10 must be equal to x plus 15. If x is 25, substitute 25 in your equation and see if they're the same. 2 times 25 is 50 minus 10. 25 plus 15 is 40. 50 minus 10 is also 40. So yes, they're both correct. So yes, it's a parallelogram. Okay, show work. Part B. That's the same type of problem. If G is equal to 14, H is equal to 5, is this a parallelogram? Set the equation up. 2G minus 11 must be G plus 3. And H plus 1 must be 2H minus 3. And if G is 14, 2 times 14 minus 11 must be equal to 14 plus 3. And obviously, that's not going to equal to itself. But let's figure that out. 2 times 14 is 28. And then minus 11 is 17. 17 is equal to, yes, 17 is equal to 17. Okay, so this works. What about H? 5 plus 1 must be equal to 2 times 5 minus 3. 5 plus 1 is 6. 2 times 5 is 10 minus 3. And so 10 minus 3 is 7. 6 is not equal to 7. So it's almost parallelogram. Almost doesn't mean it is a parallelogram. So this doesn't satisfy. No, it's not a parallelogram. Your opposite sides must be equal to each other. It cannot be close to each other. Like it's even though the numbers are close, if it's not equal to each other, not exactly equal to each other, they're not satisfying the conditions for parallelogram. Even if it's 6.666 to 7, or even if it's 6 equals 6.1, they're just not equal to each other, okay? They must be equal to each other. All right, so part A is yes, part B is no. We got more theorems in the next page. 6-14, Converse of Theorem 6-10. If diagonals of quadrilateral bisect each other, then it's a parallelogram. Okay. And if one pair of opposite sides of quadrilateral is both congruent and parallel, then quadrilateral is a parallelogram. So it doesn't have to have both pairs that are congruent and parallel, but if only one pair satisfies to be both congruent and parallel, then it must be a parallelogram. Okay, so let's use that information to investigate. Example 4, investigate diagonals to confirm a parallelogram. See if it really works. So if you're given AX is congruent to CX, and BX is congruent to DX, which basically means the diagonals bisect each other, can we prove that parallelogram, that quadrilateral ABCD is a parallelogram? Okay, so state the given facts. And by vertical angles theorem, you know that AXD is congruent to CXB, and AXB is congruent to CXD, okay? And you can say that triangles AXD is congruent to CXB, and XB is congruent to CXD by SAS theorem with the given informations and the angles, okay, SAS. And then you can say AD is congruent to CB, and AB is congruent to CD by CPCT, which means that both opposite pairs are parallel, congruent to each other. And by theorem 6-11, ABCD is a parallelogram, okay? So they're all connected to each other. All the theorems here are connected to each other. And once you satisfy one, then one that's already proven, then you have another theorem that's proven, okay? So a lot of these theorems are interconnected. Let's look at try number 4. For what values of P and Q is ABCD a parallelogram? So you know that the diagonals need to bisect each other. So if this is X, BX and DX must be equal to each other, right? So 7P plus 1 must be equal to 5P plus 3. And AX, CX must be congruent. So you also can set up an equation. 3q plus 1 is equal to 2q plus 3. And then you can figure out P and Q by solving the equation. See if you can do it by yourself. Come back when you're ready. Okay, so P, you subtract 5P on both sides, you get 2P. You subtract 1 on both sides, you get 2. So P is equal to 1. Q, subtract 2Q on both sides, you get Q. Subtract 1 on both sides, you get 3 minus 1, 2. So P is equal to 1, Q is equal to 2 is the answer. Okay. All right. Let's look at the next example, identifying a parallelogram. Now, think about all the theorems that we just looked at in this lesson and see if it can prove a parallelogram, a quadrilateral to be a parallelogram. So part A, is PQ or S a parallelogram? Explain. Okay, Q and R, they're same side interior angles. They're supplementary. Okay, 132 plus 48 is equal to 180. So QP and RS are parallel. And your theorem 6-15 says if one pair of opposite sides are both congruent and parallel, then it could be parallelogram. Okay, so PQ and RS are already congruent to each other, and you just had to prove that they're also parallel. And then you can use theorem 6-15 to say, oh, it's a parallelogram. Okay. Part B, is this a parallelogram? Well, you know that these two are congruent. Okay, but we don't know if Y, let's say this is F, YM is congruent to Y, WM is congruent to YN. We don't know that. So though diagonal WY bisects XZ, we don't really know if XZ bisects WY. It's just not enough information. So we don't know if it's a parallelogram. So you're gonna say it's not necessarily a parallelogram. It could be, but it's not necessarily. Okay, it's just not enough information. All right, so that could be an answer, not enough information, or NA. So let's try number 5, A and B. See if you can determine if those quadrilaterals are parallelogram, and see if you can explain by which theorem. Okay, come back when you're ready for answers. So the first figure here, we know that the opposite interior angles are congruent. Okay. Could we say that this is a parallelogram? Does this say anything? Well, we don't know. We don't really know if B and D could be congruent, like the angles B and D, or we don't know if any of these pairs of sides are parallel or congruent. So just having the information that one pair of opposite angles are congruent is not enough information. You really can't say anything, because even if you want to try to make a diagonal here and try to prove the triangles are congruent, you can't. You just can't, because you don't know if AB is congruent to CD. We don't have enough information. Okay, so for part A, ABCD is not a parallelogram, because a parallelogram has two pairs of congruent opposite angles. We don't have enough information. Okay. What about EFGH? 151 plus 29 is 180, right? And so we know that the same side interior angles are supplementary. What does that tell you? It doesn't tell you that FG and EH are congruent, but it tells you that they're parallel. Okay. So you can also say, by using theorem 6-15 on just like part A in this example, you just need one pair that's both congruent and parallel to each other to prove that it's a parallelogram. So EFGH is a parallelogram. So this is yes. Angles E and F are supplementary. So lines EH and FG are parallel. Let me move it here. Okay. So EFGH is a parallelogram by theorem 6-15. Okay. All right. So this one is for part A. This one is for part B. All right, example 6, verify a parallelogram. I think this is the last example. It's the application part. Okay, mechanic raises a truck using a lift. This is a lift. For safety, the floor must be horizontal and the top of the lift must be parallel to the floor. Or else your truck might slide down, right? Is the lift shown in a safe position? So check if they're parallel to each other, to the ground. Okay. So first, you need to gather some information. This one is 75. That one, the angle over here is 105. The opposite sides over here are 6. So they're congruent. So the lift and the floor form a quadrilateral. If the quadrilateral is a parallelogram, then the side holding the truck will be parallel to the floor and the lift will be safe. So finding the sum of the given angles, you figure out that these two angles, same side interior angles, are supplementary. So since these two angles are supplementary, that makes the shorter opposite legs, so the left and the right sides, parallel. So we have at least one pair that is both congruent and parallel, which means it's a parallelogram. And so you can say that the top and bottom sides are also parallel to each other since it's a parallelogram. By definition of parallelogram, all opposite sides are parallel to each other. Okay. So the lift is in a safe position. Okay, so try number 6. A carpenter builds the table shown. If the floor is level, how likely is it that a ball placed on the table will roll off? Okay, which means, is it parallel or does it have is it kind of slanted? So the ball rolls off. Okay, so see if it's a parallelogram. Basically, check if it's a parallelogram. So this one, these two sides over here, these two lines are diagonals of this quadrilateral, right? So see if the diagonals bisect each other. That's 10 inch, that's 10 inch. So these two are congruent. That's 20 and that's 20. So these two are congruent. And by what was the theorem? So by theorem 6-14, converse of theorem 6-10, it should be a parallelogram because the diagonals bisect each other. Okay. So since the diagonals bisect each other, the table legs, their diagonals, right, form a parallelogram. So the table legs over here, the opposite sides, for a parallelogram with the floor and the tabletop. And the tabletop is the side opposite the floor. So it's a parallel to the floor. And the ball is not likely to roll off the table because it's parallel. It's just going to stay, right? It has no slope, zero slope. So let's explain that. The diagonals bisect each other. So the table legs form a parallelogram with the floor and the tabletop. The table, oops, a typo here. The tabletop is the side opposite. So it is parallel to the floor. The ball is not likely to roll off. Okay, so how likely means is it almost impossible? Is it impossible? You know, like, is it gonna fall or not? How well do you think it's gonna fall? You know, so if it's parallel, it's probably not gonna fall off. But if it's a little bit slanted, then it's gonna fall off slowly. If it's really slanted, it's very likely to fall off quickly. Okay, so summary. We have a lot of properties to prove a quadrilateral to be a parallelogram. So identifying quadrilaterals that are parallelograms. The quadrilateral is parallelogram if you have two pairs of opposite sides that are congruent, or one pair of opposite sides are congruent and parallel, or the diagonals bisect each other. And also, for angles, it's a parallelogram if one angle is supplementary to both consecutive angles, or both pairs of opposite angles are congruent. Okay. So that was lesson 6-4, proving a quadrilateral is a parallelogram. Okay, that was it for this lesson. We'll continue with the next lesson in the next video about properties of special parallelograms. See you.